Okay. So today, Jose is going to be telling me, Jason, about stuff he's been working on with David. And I don't really know what that stuff is. Maybe we've talked about it before.
I like to be an international man of mystery, as you
Okay.
know.
Do we have a title or
Let's call this coalgebraic modal extensions of logics.
coalgebraic modal
There is a
extension of logic?
hyphen, so something along these lines.
Okay.
The
Okay.
hyphen doesn't really come across when I just say it out loud.
Right. So the modalities are, in a sense, coalgebraic. Is that the point?
So the
Uh,
point is that just should give us a motivation, right? So one motivation that we worked on a while ago was in a situation where you have some sort of base logic that is sort of boring. So you have some category C that serves as contexts for some logic.
mhm.
So this could just be sets. So for each set, you tell me what are the sort of primitive propositions about these sets.
Mhm.
And one way to say this is that you have this contravariant functor P, and this could take values in any category in principle, could
Yeah.
be sets and so on. But for the sake of generality, let's say we think of the primitive propositions as objects of D. So
Okay.
this could be just a set of primitive propositions in case D is set,
Hmm.
or it could be a post-set of primitive propositions if you want to presuppose that you have a notion of sort of implication between these. So,
Right.
every in every situation where you have this primitive proposition hold, this other one should hold, and that sort of induces a ordering
Yeah.
in your set of primitives. So we're leaving it open for now. We don't know much about D,
Hmm.
and that's fine because one situation is that you don't assume anything about the logic aside from the most basic things you could possibly have. For us, the most basic things would be we can perform substitution. So the idea being that if I have a formula phi, and this formula phi is a formula phi of some y,
Hmm.
and I have some function that tells me if
So
I
this is
have,
y as an object in C and uh
yeah,
right, okay.
if I have a function that tells me that if I take an element of type x,
Hmm.
then out of that I get an element of type y, then you can think that out of a formula phi about things of type y, I can get a formula phi about things of type x by just saying it's phi of f of x.
Right.
So this performs substitution, and that is just via p. So we are thinking about phi as something in p of y here, and this gets mapped to something in p of x.
Right.
So we're assuming we can do substitution of terms, right? So
Hmm.
morphisms in C, our category of contexts, tell us how you convert terms of type X into terms of type Y, and then
Hmm.
we can use P to perform substitutions in logical formulas.
Right.
So that is sort of a bare minimum that you
Hmm.
could ask. But in our case, we want to go slightly beyond. So
Mm. And that structure is already built into this idea of this
yeah,
pseudofunctor, right?
exactly.
Okay.
Yes. So just having the fact that P is a pseudo-functor, you can do these substitutions.
Hmm.
And then, of course, you could ask for more things, but just to mention some things you can do with just these basics. So if C has enough structure, for example, C is Cartesian,
Hmm.
you might have things like, a diagonal map that you can substitute over,
Yeah.
and that gives you an equality predicate. So these things are already built in.
Right.
Um, if Yeah. So the other thing that we might like, so there are a few things at the level of logic, right, that you might
Hmm.
want to assume as extra data. So one is, okay, we have these primitive propositions. Can we get complicated propositions,
Hmm.
right? And the usual way you do this is by adding connectives and quantifiers.
Right.
Adding connectives um, is something that involves extra structure on each of the fibers P of X.
Right. So if I want to take conjunctions of predicates that come
Exactly.
fiber-wise,
Yeah.
that's
So
just structure on the objects in D.
in D. So if we have, for example, two primitive propositions, it's raining, or I don't know, the dog is happy.
Hmm.
You might want to build more complicated things like it's raining and the dog's happy, or
Mm.
if the dog's happy, it implies it's not raining, or things like that.
Yeah.
And that would presuppose that each of these px's have some extra algebraic structure.
Hmm.
And there are two things you could say. You could either assume as a property of P that all the px's have these extra structure. So that would be assuming more about P.
Right, like D objects in D need not have that much structure, but P happens to pick
Exactly.
out the
But
structured ones.
specifically the ones in the image of P might.
Okay, so maybe D is posets and P just happens to land in like Boolean algebras or something.
Yes, exactly. So it could just be, as you say, that P um, just ensures that for every x in C, P of X is a special kind of object in D. So it could be like a monoid or, a Boolean algebra or a Heighten algebra or something
Hmm.
like that. So this is one thing you can do. Um, so that's one way you can make this data more just richer. So one is assume that P has fibers with extra structure.
Hmm.
But and that gives you connectives in the logic. Um, or you could also think about quantifiers as another thing you might want to add to your logic. So for today's talk, we'll only focus on existential quantification,
Hmm.
but many of these considerations would apply for universal quantification as well.
Hmm.
And the traditional view is that quantification occurs as an adjoint to these substitution maps. So here we have PF,
Hmm.
and the idea is that if PF has a left adjoint, that plays the role of existential quantification, and if PF has a right adjoint, that plays the role of universal quantification.
Right.
And you might think about how these adjoints, if you assume they exist, relate to the rest of the structure. So there are two core things you want to assume whenever you want to think about quantification. One is that these quantifiers play nicely with the substitution operation from a logical perspective.
And those are sort of Beck-Chevalier
Yeah.
conditions.
Yeah. So what that means in sort of intuitive terms is if you pick a formula, you might want to first replace a variable with something and then do an existential quantification on whatever remaining variable you have that is free.
Hmm.
Or you might want to do it the other way around, right? So first you quantify over a free variable, and then you perform a substitution on something else.
Yeah.
And in the ideal world, these give you the same thing because the variables intuitively don't really speak to each other, right? There's no dependency between the variables.
Hmm.
So that is captured by the Beck-Chevalier condition. So this is a property you ask of P.
Hmm.
And the other property you might want is that these quantifiers play nicely with the connectives.
Yeah.
So this is a condition involving the fibers of
Yeah.
P.
Sorry, I do have a question about the Beck-Chevalier. So we've, um, I guess in when I've seen you talk about this topic before, you talk about existential quantification. and then there's universal quantification. If
Mhm.
you have Beck-Chevalley for like existential quantification relating to substitution, does that at all relate to whether you have it satisfied by the universal, or is there
As long as universal quantification exists, then yes, it's automatic, and that's just because adjoints compose. So if you write down the satisfaction of the Beck-Chevalley condition for this adjoint pair,
Mm-hmm.
it gives you a commutative diagram,
Yeah.
and everything in the commutative diagram has a right adjoint. You take those, well, the right adjoint of exists F is just PF,
Right.
and then the right adjoint of PF is
I
for P.
see.
So you get Beck-Chevalley for
Okay.
universal quantification.
Right. So either implies the
Yeah.
other.
So you just need to assume one of them as long as the quantifiers exist.
Right. Okay.
This can get slightly trickier if you assume that it only exists for some f's, and then of course you can say universal quantification for f holds whenever Beck-Chevalley for existential quantification for f holds.
Right.
But anyway, it will be f-wise.
Right.
All right, so in principle, you have these two conditions you might ask of the quantifiers, right? So quantifiers play nicely with substitution, and quantifiers play nicely with connectives.
Mm-hmm.
The latter is what's called the Frobenius reciprocity condition. Um, but
And by connectivity, you mean like a monoidal product, or is there some more?
typically, yes.
Mm-hmm.
So as I mentioned, you might want each of the fibers PF to have extra structure to give you quantifiers like and. So
Mm-hmm.
because it would be something like this. So phi and psi get mapped to a new connector, a new proposition phi and psi, right?
Mm-hmm.
Um, and typically, if you want this to behave as usual logical conjunction, you do want this to serve as a monoidal product on
Mm-hmm.
Px.
Right.
So that sort of makes Px a monoid in D
Yeah.
with this operation, and it's a Cartesian monoidal structure.
Yeah.
But a priori, there is nothing forcing you to consider this as the notion of conjunction. So in principle, you could have some other tensor product that is not Cartesian,
Mm-hmm.
and you could still ask that it plays nicely with existential quantifications.
Right.
So
Yeah.
you can still ask for Frobenius for any kind of monoidal structure on the fibers.
Mm-hmm.
Okay. So our starting point could be this, right? So we start with a scenario like this, where you have a base notion of logic that we're calling P, and maybe it's very bare bones. So perhaps you don't want to assume that you have any connectives. Maybe you want to say you can do existential quantification and that it plays nicely with substitution because you always have substitution as the bare minimum. But maybe you don't assume you have any connectives. You're just determining which are your primitive propositions. Well, there are two things you might simultaneously want to do. One is you can change the predicates and try to get a richer form of logic. So in our case, it could be adding connectives to the logic that you didn't have before.
Sorry, is this adding connectives to the logic? So is this like adding structure to D, or
Yeah.
where's the okay.
So one way we can do this is by specifying a monad on D
Right.
and try to think of, well, I had my usual predicates, Px,
Mm-hmm.
and they're bare bones. Maybe I can take the free L algebra on Px,
Yeah.
and if L is carefully selected, that will give me new logical connectives. So L could be, for example, the free Boolean algebra monad, and now your free algebras on P are, the free Boolean algebras on Px.
Mm-hmm.
So the idea being I have all my primitive propositions, but now I have all the other things I could possibly build out of them by using Boolean connectives. finitely many times.
Right. Is the idea that we'd then get some other map, like P bar into L alg or something? Is
Mm.
that a
Well, you do. If you
just
think
like
about it,
free?
you can just, yeah. So if you just have C op P into D, then the free algebra functor will take values in Kleisli of T of L, right?
Right.
Which
Yeah.
of
Yeah.
course embeds in L algebra.
Right. Okay. Right. So you might start with some weak notion of your predicates, and then you want to like freely add structure
Yeah.
to those. Okay.
So you're freely adding connectives.
Mm-hmm.
So you didn't have, say, let's say you're working with the situation where you didn't have any connectives at all. So
Mm-hmm.
here maybe D was just set. And for each X, you were just telling me what is the set of primitive propositions
Right.
or things I might consider about X.
Mm-hmm.
And now when I look at, say, this free Boolean algebra on Px, I'm saying, well, I'm looking at every possible formal
Yeah.
formula I can build out of these primitives with finitely many Boolean connectives. So
Right.
these, in a sense, is the world of all the classical things I could say about
Yeah.
those objects. Okay, so that's one direction you could go, right? And that's just enriching the logic to add more connectives and more ways of differentiating between the behaviors, right?
Mm-hmm.
When you talk about semantics, those things come to life.
Yeah.
But a different thing you could look at is changing the contexts.
Yeah.
So perhaps you're working with a rather bare-bone form of context and you want to consider something more interesting. In our case, notably, instead of trying to think about formulas about interfaces of a system, for example, we might want to talk about formulas that hold off the system. So say the system has a certain behavior,
Mm-hmm.
that would be, a logical formula that applies to the system as a whole rather than to any interfaces in
Right.
particular. But how do you do that? Well, in a very similar way. Instead of having a monad, here we want to have a comonad because by looking at the coalgebras for this comonad as your um, contexts, well, we know that coalgebras for comonads serve as a good notion of system very
Mm-hmm.
often. So the idea is I'm having some comonad F. I'll just write this as F all for reasons.
Okay.
Okay. So we have a comonad on C,
Yep.
and if you think about coalgebras for this comonad as systems with interfaces given by objects of C,
Mm-hmm.
then, well, you might want to think, what kind of logic can I produce that has that as context? One important thing to note is that, of course, when you move from C to coalgebras,
Mm-hmm.
you no longer necessarily have the Bakhsh-Chevalley condition or anything like that, or even,
Right.
uh, it's not clear how you just extend P to a logic on coalgebras.
Right. So I get like it's similar to what we had before. I guess we could just take F coalg op, which has a map, which like I guess just takes the interface of the system and
Mhm.
does post-compose by P, but P was meant to have some special structures that,
Mhm.
the composite may not have anymore.
Exactly. So, what do we do with this? So, one of the challenges is that, of course, we might want to do both of these
Mm-hmm.
things at the same time.
Mm.
So, case in point, let's say that
Oh,
P.
yeah. Sorry, I do have a question. Was that not an issue when we um like when we did the other thing, which is sort of like extend. So maybe we get a map into um Boolean alg by taking free.
Mhm.
Um now is
Yeah.
Is there a risk that we lose like Beck-Chevalier or like this the Frobenius property
Well,
automatically?
until you have the connectives, it doesn't make sense to ask if Frobenius holds, right?
Sure.
But it could be that you had some connectives given by P already
Hmm.
and Frobenius for those, and now you add more connectives by taking the free algebras. There
Right.
is no reason a priori for you to expect for Frobenius to hold about
Right.
those new connectives. In fact, if you think about it, um, there is nothing special in principle about any of the new connectives added by this free algebra.
Right.
So you can't even single out, say, a conjunction. So take the free Boolean algebra case. We might think that this one is special, but how can we single it out compared to, I don't know, or implies?
Right. Yeah. Yeah.
You know,
Right.
in
Okay.
principle, there is no reason why we would look at this one specifically.
Right.
But this is a problem we can discuss later.
Sure. But on the so the Beck-Chevalier, does that maybe just work? Because we're just now taking like some two functor.
We're doing a restriction, right, when we do this.
Doing a restriction. Um, what do you mean by that?
Because we had a Beck-Chevalier that held for all the p-axes.
Hmm.
Um, and now we're asking, um, yeah, okay, a priori, you don't necessarily need to have Beck-Chevalier for the new thing.
Right. I mean, it's sort of like the Beck-Chevalier says that a certain two cell is invertible, and it seems like if you just apply some two functor
Yeah,
to that thing, that might
yeah.
actually be
If
preserved. Because like the other thing is like, do you even have existential quantification? But I guess that also similarly, like you're applying a two functor. If you've got an adjunction in here coming from PF and exists F, then that should be mapped to an adjunction by post-composing with that two
right, I see.
functor, I think.
Yeah. I mean, in any case, you will see the approach that we'll take will make
Mm,
that a bit
right. Okay.
clearer.
But it does seem like that it's more of an issue on the left-hand side,
Yeah.
looking at F coalgebraics
And
than
that's fundamentally as well because Beck-Chevalier only applies when you have a given pullback in C. So
right.
we would have to be looking at the pullback of coalgebras to begin with.
Yeah, okay.
And yeah, as you know, F in principle doesn't preserve pullbacks.
Mhm.
Anyway, um, right. So you might want to do these two things at the same time. And the sort of motivating example would be that you start with your bare bones classical logic. So maybe C is some category with interfaces, and P, each PX is a Boolean algebra.
By C is some category with interfaces, you just mean in a sort of vague
In an abstract
the
sense,
systems.
yes. Could
Okay.
be just sets or whatever, finite
Right.
sets.
Okay.
Um, and then maybe G is sets, but every PX is a Boolean algebra. Let's assume that's the case.
Okay. So does that mean that PF, I mean, so one difference between asking for D to be the structured category and merely asking for P to land in, structured objects
Yes,
is
there
that
is.
like, are we asking for the image of morphisms to land in structure preserving morphisms?
We so mm,
I mean, for Boolean algebras, there is by asking for existential quantification, you're
we
automatically
don't.
asking
Yeah, no, we
uh,
don't necessarily want that.
okay. But we will
Um,
we will get preservation of a conjunction for free, right? Because
we
of
will, yes, by adjointness,
Mhm.
yeah, and disjunctions, I suppose. But anyway, so each of your p-axis is already a Boolean algebra, so you can do like classical logic. You can
Hmm.
talk about not phi and psi and phi
Yeah.
implies psi, all that stuff. But perhaps you are interested in something slightly different. Perhaps you're interested in temporal formulas. So now, aside from having these connectives and having quantification, you want to have a temporal semantics and a temporal syntax for these things and write formulas like eventually it will be true that phi, and it's always the case that phi,
Hmm.
and so on. Well, that will require adding some more stuff to your syntax so that you can express these things.
Hmm.
And that will, of course, have the advantage of enabling you to have more semantics for it, which is the ultimate goal here.
Right.
So we need to add the possibility of having predicates like globally phi or
Hmm.
eventually phi. And that's where our monad L comes in. So
Right.
you might have a monad L that freely adds these things.
Hmm.
I won't get into the details of how you construct this, but if you take your favorite temporal logic that has a sound calculus, sound and complete calculus for it.
What's that?
So you have a set of axioms and ways of writing proofs. Okay, so you have rules for writing proofs,
Right, okay. So not just syntax, you have like inference.
inference rules, indeed. So you have, rules for writing a proof in the logic. And in a sense, these rules capture fully all the possible behaviors of models. So
Capture all the possible behaviors of models.
if something is true in all the models, then I
Hmm.
can actually find a proof for it.
Right. Okay.
So for certain kinds of temporal logics, you do have these. So LTL, for example,
Hmm. What's a
and
model for LTL? So,
you
yeah.
could think of streams.
Hmm.
Yeah. So sequences.
Right.
But I don't want to get
Oh,
too carried out on the digression here. But
right.
the point is, if you have such a nice proof calculus,
Hmm.
then you can do a Lindenbaum-Tarski style construction
Hmm.
where you take all the formal formulas you can build with the new connectives and the old
Yeah.
ones, and then you quotient them out by an equivalence relation based on the provability relation.
Right. Okay. Um, so sorry, going back to, so a sound calculus.
Sound just means anything that you can prove holds in every model.
Right. So do you have to start with a notion of like model for
Yeah, when you say sound, it's sound relative to a semantics.
right, okay. So like if we're talking about the like syntax for Boolean algebra, we only talk about like whether our calculus is sound once we decide that, this symbol is actually meant to be conjunction in Boolean algebras and so on. Okay.
It's
Is that
more so soundness for the classical stuff would be like if I have a proof of this thing, then it's
mhm.
true in every Boolean algebra.
Right, okay. But I need to say that like these are meant to be interpreted in Boolean
Yeah.
algebras.
Yeah.
And with respect to
Yeah.
that,
So just to illustrate, if you had intuitionistic logic, for example, then you have multiple different semantics you could use. So one is heightened algebras, but
mhm.
there's also like Kripke frames.
Uh-huh.
And you can talk about soundness for each of these or completeness for each of these semantics.
And are we going
So
to get like different inference rules depending on the
Well, for these, we're still using the same rules.
okay.
But in principle, you could have a really bad semantics that it's still sound, but you don't quite have enough stuff to be able to capture the full behavior. So, like, being true for every model doesn't necessarily mean that I can find a proof in my system.
Right.
Like, trivially, I don't know, imagine your semantics has literally just one terrible model
Hmm.
where everything's true.
Okay.
Then of course, being true there doesn't mean that I can find a proof in my system of a fact.
Right. So I could like take the sort of syntax for like intuitionistic logic and declare my interpretations to be Boolean algebras, and then I'll find that like actually I'm missing law of excluded middle or
Mhm.
something.
Exactly.
Um, okay, sorry for
Very
that
good.
digression, but
So right. So here we we can build a monad for LTL, for example, and the underlying set for the monad is just for like LX would be something like take all the formal formulas,
Mm-hmm.
finite formulas you can build with all the Boolean and temporal connectors,
Mm-hmm.
then quotient them out by a relation that say these two formulas are equivalent if I can prove that they are the same in LTL. And the
Mm-hmm.
reason why this works is that you have a finite set of rules that you can use that has this completeness property. But I don't want to get into the
Okay.
details of this.
Do we also need to like add um like um morphisms based on the inference rules that should hold for, so we take our posts, so maybe like D is just post sets or something.
Yeah, no,
Um
the maps will be like connective preserving stuff.
mhm.
Like morally, we're trying to produce the free LTL algebra on
Right, okay.
X. That's kind of like what we're
Right.
trying to
And more,
build.
okay, so morally like one formula will be less than another formula if I can derive a proof.
Yeah,
Okay. Right.
yeah.
And then I guess that gives us a pre-order, and you're saying we more of a quotient term,
Hmm.
equivalent terms. Okay.
Absolutely. So yeah, so the thing is, um, you might ask if a temporal formula is true, but when you're talking about temporal formulas, you can talk about them as capturing behaviors of a system. And then you might think, instead of just amplifying P to temporal predicates, I can also at the same time change my context to coalgebras to talk about temporal formulas on systems.
Right.
So we want to do these two things at the same time, and that's sort of the motivation for this whole discussion.
Okay. And is there just like vaguely before we go into detail, is there some reason like we have to do them at the same time rather than independently? Do they interact in interesting ways?
Yes, the gist of it is if you keep P as just looking at interfaces, you don't necessarily get a a proper logic.
Okay.
Because like I guess you can talk about the formula holding forth an interface at a given time, but that's not as interesting as saying that the formula holds for the system at a given time.
Right.
Anyway,
And sorry, one more question. So I guess we're maybe like being uh vague about like what precisely like I assume we're not going to go into detail about like what the inference laws are for LTL and or L is meant to be some general logic. Are there like is this well studied? Like do people have names for the structured categories you get from
for temporal stuff.
yeah.
There are a few approaches, like categorical approaches to temporal
Mm-hmm.
logics. So there are these things called fan categories that serve as models for one of the intuitionistic temporal logics.
Mm-hmm.
But I have to say, this doesn't seem to be as deeply explored in the categorical side of things as some of the other kinds of uh, modal style logics.
Right.
But yeah, so Valeria in Topaz has done some stuff on this, for example, with some collaborators. And I think there's one more paper that I can't quite remember now, but as far as I can tell, this is still not as explored as you would like.
Right.
Yeah. But yeah, you could be looking at semantics in fan categories as well for this if you go
Right.
intuitionistic.
And
Anyway,
so L might be like the free fan
yeah,
category functor or something. Okay.
yeah. Assuming that exists. I think um can't quite remember now if their paper sort of implied that there is such a thing. It's been a while since I looked at
Mm-hmm.
it, but anyway. Right. So how can we then talk about these things in a sensible manner? So there are two sort of things I want you
I'm gonna
to
try
do
and
before we
get the light tab back. There we go. Okay.
okay. So there are two observations that I want to make before we really go into that.
Mm-hmm.
And the first one is that here we're working at the level of functors between categories and building monads on that. And that has sort of the disadvantage of having to keep track of Beck-Sheveley all the time and
Oh.
talk about the existential quantification as a
Mm-hmm.
separate functor all the time
Yeah.
and so on. But we have a nice easy fix to that. And my easy fix is that we're actually going to work, oops, let me change the color again, with double categories instead. So now we assume that we have a double functor. In fact, I will say something technical now, but you may pretend that this is just a double functor for the whole rest of this. It's actually a double pseudo functor,
Which is not the same as
which is
its.
not the same as a pseudo double functor. Yes. So double pseudo functor means that it's pseudo in both the tight and loose directions.
Okay. So, okay.
Let's leave it at that.
Sure.
And the reason why is because even when we go back to this situation, P might not necessarily be a functor, it could be a pseudo functor, and we want to keep that when we move here.
Okay.
So the reason why it's nicer to work with double categories for the purposes of this is that it turns out that a hyperdoctrine, in the sense that we have existential quantification satisfying Beck-Shevley, is
Oh, sorry. And
equivalently.
so the thing, this P up here is like, is a hyperdoctrine or everything,
Yeah.
all the.
So let's call this an existential hyperdoctrine. So by that, I mean we have the existential quantifiers and Beck-Shevley. We're not assuming anything else.
Right. Can I just ask? So I've never really understood the term hyperdoctrine, but I understand the term doctrine as like being some sort of higher notion of theory, and like one way of describing such a thing is as a two monad on a two category. Where did the Do you know where the term hyperdoctrine comes from? Why?
Levere, and I'm not entirely sure why it's stuck. I personally find it confusing.
Okay.
It could just be that Levere was actually thinking in the sense of two monads,
Right.
as like an analogy kind of thing.
Okay. Because I guess it
But
is taking this like so like two monads, you can talk about algebras for, and that's like a category with extra structure if you have two monads on cat. And this is giving us like a category of context with some extra
yeah,
structure, but in a more complicated way.
so as far as I can tell, that's why. But I have to admit that I'm not super happy with the terminology. But
Okay.
we gotta pay Levere his respect.
Sure.
So right here, we were just looking at an existential hyperdoctrine. So PF has a left adjoint for each F, and we satisfy Beck-Shevley. So the thing is, as it turns out, specifying this data is the same as specifying a double functor from span C up into, I guess here we had D. I'll just say some double category D. I won't get into details on this.
Right. Okay. But
But
if
it's
we okay.
probably, yeah, just cat.
So the idea of we're folding in the existential, we're folding in some of this extra structure into the actual data of a functor.
Yeah.
Um,
And basically all the calculus involved with Beck-Shevley is already fully contained in the double category of spans. And then, yeah, I mean, I won't get into the details of this, but if your double functor is a nice enough double functor, which, I mean, if I'm just calling it double functor, then it is, but if it's at least a pseudo double functor or even a unit, like a normal double functor, unitary, then, span has companions and conjoints, which will get preserved by this double functor, and that's how you get the
right. So if it like as a special case, if D were like quintet of some two category
yeah, I
D.
mean, here this will usually look like quintet of cat or something like that, but
Right.
I want you to leave D open for now.
Okay. But so like I can see that. So in span, I've got like in particular two special spans, one which is like identity and then F, and then I've got like F going backwards. And I guess I can see that if I want to define a map from span into D, then I need to give like a forward going map for F and a backward going map for F. And I guess is that that's gonna, if I do this in the right way, I'm gonna get like some adjunction property. And I guess that comes precisely from the fact that these are companions and conjoints of
Exactly.
other type.
So in span, every map F in C has both a companion and a conjoint, and in fact, every span is a composite of a companion and a conjoint. And your double functor will preserve companions and conjoints. So if it lands in quintet, you will get, well, companions and conjoints in quintet, and that will give you your adjunction and just the map.
Yeah.
So that's how you get like both the substitution as just like the image of the companion under your double functor,
Yeah.
and the conjoint will be your existential quantifier.
What if you want like all three? You want a universal quantification as well? Is there some?
Well, I guess you have to look at conjoints for the
Yeah, right.
other,
Okay.
yeah.
Okay.
Anyway,
Oh, I
so
guess we should say that C the whole time was meant to have pullbacks, and so you can form this.
sure, yeah. So we assume C has pullbacks so that we can compose spans. Or at least enough pullbacks, but I don't want to get in the whole digression about adequate triples. Yeah.
Okay, can I, sorry, just another digression, but like, what if I did cospan instead of span? Because that still has these companions and conjoints. Well, okay, actually, maybe I know the answer because cospan of span, cospan of, or span of C up is going to be like cospan of C up or something like that. So it's really the same kind of construction.
Although here we kind of want C to be Cartesian rather than co-Cartesian, so let's work with span and have the C side.
Okay. And we should say that op means vertical op.
Op means tight op.
Right. Okay, sorry, tight, yeah.
Yeah. All right. So the whole point of this whole discussion and digression is that instead of having to work with P and keeping track of whether constructions we do with P still have Back-Sheveley and existential quantification, we can instead work at the level of double functors or double pseudo-functors. And then if we want to recover the usual hyperdoctrines, we can just look at the case where we have a double category of spans as C, and we have a quintet double category in the codomain.
Right.
But that justifies working at this level of generality. It actually simplifies things quite a lot. Okay, so we work with double categories now, and we still want to follow the same idea here. So we still want to monadically add connectives. So we want to still talk about monads in D, but now these are monads in the double category D, on the double category D. And we still want to talk about comonads on the double category C. Okay. Now, what sort of thing would we be interested in? So we're saying, with a situation like this, which I'll call a coalgebraic-modal extension context, the ideal scenario is that we can extend P to a new logic on coalgebras. So we want ideally to go from here to having coalg F op and some P star. And here we have alg L.
Right.
And we want this ideally to still be a hyperdoctrine. So that would accomplish the goal of changing my context to coalgebras and changing my predicates to algebras so that I have the extra connectives. And I still would have all the logical structure because this is still a hyperdoctrine of whichever kind I'm targeting.
Yeah.
So I would still have existential quantification, for example.
Right.
So this would be nice. That's the dream.
Mm.
But
And this,
how
sorry, and this is so the name coalgebraic modal is that
this is the
referencing these two?
coalgebraic bit, this is the modal
Okay, right.
bit.
Okay.
And that's why there is a hyphen.
Okay.
And we are extending the logic because P star can be seen as an extension of the logic of P.
Right. Just so F is a comonad on, or
C.
maybe just endofunctor. Are we talking about coalgebras for?
Well, in this situation here, I mean, that's not a big distinction because
Hmm.
we can always look at the co-free comonad if you just
Hmm.
have an endofunctor and
Right. Okay.
things
Okay.
about that instead.
Mhm.
Just as an addendum on the temporal logic stuff, that is kind of what happens. So if you look for the co-free comonad on the identity functor,
Mm.
that gives you the stream comonad.
Oh, okay.
So you would be talking about temporal formulas on streams.
Right. Okay.
Yeah.
And this is so if F is a comonad on C, then F op is a monad on C
Mhm.
op. Okay, so this I could, if I wanted to, think of this as alg F op,
Yeah.
perhaps. Okay, which is kind of interesting.
Yeah.
Okay.
Okay. So here's how I think is a sensible approach to this. So working at the level of the double categories,
Mhm.
we will build a new true category. And the interesting stuff that we'll be interested in will happen when we look at um, monoidal monads in this true category.
Right.
So the idea is, okay, so first of all, let me describe to you what this true category is. I'll give a very concrete description first, and then I'll do a slightly more abstract one. So the concrete description is that the objects of this new true category that I'll call doct, the true category of doctrine.
Okay.
So its objects are double pseudofunctors between Cartesian double categories.
Yeah.
Okay? But, um, so, the reason why we can think of these objects as doctrines is going back to what we saw before. It's a generalization of this situation.
Hmm.
So they are doctrines in abstract.
Right, or hyperdoctrines and
Yeah,
abstract. Okay.
yeah. So in particular, it includes, this is an extension of all the usual classical regular hyperdoctrines because those are just the ones where bold C is spans
Yeah.
and bold D is quintet. Um, our one morphisms, I'll write in blue,
Hmm.
okay? Our one morphisms are triples. So let me put a 0 here. And
This is referring to the not the.
to object one, because this is an object.
Okay. Right. Okay.
Um, and if you prefer, I can do 1 and 2. If you,
Oh no, I don't mind. I'll just is this
in case
certainly
it gets
isn't the.
confusing with like tight and loose, because sometimes they're a little
Yeah,
bit.
yeah. No, I understand. Just
Okay, so when I say D0 here, I don't mean the tight
yeah, yeah.
part of D. I'm just saying this is object 1 and object 0. And then I have P1 here. So this is another object. And okay, so a morphism consists of a triple consisting of, well, I'll write this as just a diagram in double pseudo tight. So F, I should write this as F op. F and L are just double pseudofunctors.
Hmm.
Um, Rho is just a tight transformation.
Hmm.
Okay.
Yeah, okay. Double. So I just I'm just going to register that I'm sort of concerned about default pseudo functors because where everything's pseudo, um, is there like um, a nice way of thinking of those in terms of like double functors or internal categories and sorry, double categories of
I
categories
guess
and
you
cat.
want that in weak catch.
So category of
Yeah.
category. Okay,
Anyway,
it's okay.
um, right. So FOP and L are double pseudo functors, or if you just want to simplify
Mm.
things, pseudo double functors.
Okay, but there is
And
some two category of those things and
yeah,
type
yeah.
transformations. Sure.
And rho is just a tight transformation.
And sorry, you said that C, D, these all need to be Cartesian
Yeah.
double categories, and the functors presumably need to be morphisms of Cartesian.
No, they're
Okay.
just double functors.
Okay.
Yeah. And a Chu cell, so I'll put it in red. Oops. So let's say I have some F tilde and some L tilde, and I apologize for the terrible notation. I'll move this out a little bit. And I have some, well, rho tilde. I'll write a better diagram in a bit. But the data of the Chu cell is just transformations of F and of L
Hmm.
that make a cube commute. So my cube looks like this.
Well, your cube has sort of flat or identity
So let me just,
faces.
yeah, exactly. So I'll just draft the cube. L tilde. And then here I have rho. And then here I have alpha F. Here I have alpha L. And here I have rho tilde.
Right. Okay. And so, and this is right.
So
This is so alpha F goes from
so
F.
conditions on Chu morphisms.
Right. And just yeah, to be clear, alpha F goes from F F tilde to F or something,
Yeah,
and therefore alpha
maybe
F.
I'll write alpha F on.
Okay. So this almost looks like this two category of like
Yeah,
lax
yep.
uh
So
okay.
I'll tell you exactly what it is. So this is Chu cat lax delta 1 Cartesian double pseudo tight op op.
Hmm. Okay. And two cat lax, I guess that's um that's functors are two functors, but transformations
Mhm.
are lax. And
So what is the cool thing about this? So there are three nice things about this Chu category doct. First of all, this is a Chu category of lax functors from a small Chu category,
Mhm.
taking values in this thing. And because of that, it has lax limits.
Mhm.
In particular, it has Eilenberg-Moore objects. So if I give you any monad in doct, I can take its Eilenberg-Moore object which will be an object in docked and therefore a hyperdoctrine for free.
hmm Sorry, so we're observing that this two category has some nice properties from its construction,
Mhm.
and the point is that
So that's just one of my 3 points about
oh, okay, okay.
that.
So
So point number one, that
yeah,
has Eilenberg-Moore objects.
has, okay, and so um objects, um uh, um right, because this is a category of Lex. Oh, I know we've had this discussion a few times, but I guess this is a category of algebras and lax morphisms for a two monad, right? Because in general, if you've got two cat uh, two cat lax from any category A and B, then that is, yeah, your lax transformations are lax morphisms of certain algebras for two monad. And so there are certain properties that such lax um, categories of two algebras and lax morphisms have, and one of them is they've got certain classes of limits. But I always think that the lax two alg t lax should have oplax limits or something, and this is an EM object is a lax limit, right? So
Yeah, it's a lax limit.
yeah,
Yeah, the point's more like this is a true category of lax functors with small domain.
two category of not lax functors, right? It's strict two functors and lax transformations. Because
Yeah,
like
yeah, yeah,
yeah,
yeah,
we're
yeah,
not
yeah.
getting like monads living over each of these things. Just yeah.
Yeah, so the point is this has Eilenberg-Moore objects, and therefore, as long as we can specify a monad in docked,
Mm-hmm.
I can take that Eilenberg-Moore object for that monad,
Uh-huh.
and that will be a new hyperdoctrine because it will still be something of, well, still be an
Yeah,
object of
yeah.
docked.
Okay, right. Yeah, so EM object, that's we should just
That's what we
clarify that
are.
like alg T is an EM object. It's yeah, the Eilenberg-Moore category. Sorry, I think maybe so usually Lex this actually looks to me like it's collax. Do you right? Because like a collax transformation has components, phi A, phi B, and then you got like FU, GU. So lax, I mean, like there are, people use different conventions, but typically lax goes in this direction. Here it looks like we're having the two cells go in this direction, which is what I would typically call collax. And it and but in particular, having the two cells go in this direction does mean that you have collax morphisms for two algebras, which does mean you have lax limits. So I think this makes sense to me, but
Yeah, it is very possible that I
yeah.
swapped that out the codes. As you know, I'm terrible with all the codes.
Well, I think the issue is that lots of people are, and therefore both terminologies exist in the literature.
Yeah.
But in the very case, I'm just like saying, yes, I now understand why it should just be true by sort of abstract nonsense,
Hmm.
like I believe a paper by Lack, called Lax or Limits of Laxamorph. One of Steve Lack's
Yeah.
papers in the early 2000s proves that T-alg Colax has all lax limits and T-alg lax has all colax limits. This is a lax limit. I believe it's living in something of the form T-alg colax. And so, yeah, I believe that now. Okay.
Cool. We should go over that at some point and make
Mhm.
sure it's right. But yeah, so far so good. We're sort of running out of time, so I'll try to make the two last points quickly and wrap it up. So first, it has Eilenberg-Moore objects. So the question is, as long as I can find monads on this, right? I
Mhm.
can take Eilenberg-Moore objects, and that will be a new hyperdoctrine. And as you can imagine, because of the construction of doc, the Eilenberg-Moore objects are sort of computed component-wise. So
Mhm.
actually, I'm looking at, in the case F is a comonad and L is a monad, I am looking at contacts given by coalgebras and um,
Right.
predicates given by
Okay.
algebras.
Right. So the first one is that monads in here look like pairs of monads
And the
and
row
thing.
becomes lax morphism of monads
Ah, okay.
between them.
Is that point number two?
No,
Oh, okay.
that's still part of point
Can
number
I do
one. It's
1.5?
just that
Okay.
there's a lot sort of bundled in
Uh,
point number one.
okay.
So yeah, so monads in doct
Hmm.
actually give you lax morphisms of monads
Hmm.
between well, I guess algebras for F op and algebras for L.
Right. Oh, okay, right. Comonad F um on C, uh
Plus
a
monad
monad L
L on
on
D
D.
plus a lax morphism of monads from F op to L. And this, mind you, this lax morphism of monads, going back to the temporal logic thing, is the temporalization map that tells you how you interpret the semantics for a temporal formula.
Oh, okay. Oh, right. That's what we want, right?
Mhm,
So a lactmonad map gives a morphism from algebras for F up, which are coalgebras for F, into algebras for L. Algebras for F up are meant to be our systems. Algebras for L are meant to be our extra structured
mhm,
categories, things which you can interpret LTL in. Okay. Okay, that's quite satisfying.
mhm. All right, so point number two.
Mhm.
So what is a monad in doct, really? So we're trying to say that it's, well, what you put out as point 1.5,
Mm-hmm.
but let's actually say it in abstract nonsense for a moment.
Mm-hmm.
Specifying a monad structure on an object P, right,
Mm-hmm.
is precisely the same. I guess you did write it as 1.5 in a sense. It's precisely the same as specifying that. So I guess point two was going to be slightly more general to point
Okay.
1.5.
Okay.
I'm actually claiming that these are basically synonyms, right? There is an equivalence between monads in doct and such triples.
Okay. So I'm going to say I'm going to add a precisely to 1.5 and then call
Or,
it 2.
or,
Does
or
that
rather
work?
just call 1.52 and say R equivalently
Okay.
or
Equivalent.
precisely,
I'm going to go with
whatever.
precisely. Um,
And you can call that point two now.
okay. Okay.
And point three is that the symmetric pseudomonoids now. So,
Mhm.
so first observation, doct is a Cartesian two category.
Docked is a Cartesian 2 category. Okay. I because its
Yeah,
components are Cartesian.
yeah. You
Sure.
just multiply uh
Okay,
like
sorry.
yeah.
The Cartesianness for docked, sorry, it has nothing to do with the Cartesianness of C and D. It's
No, no,
to do
it
with the
Cartesian
Cartesianness
and
of
so yeah, so like if I have some C op, some P from C op to D and some Q from C prime op to D prime op,
Mm-hmm.
I just multiply them
Yeah,
together
yeah.
and
Okay.
that's Cartesian product here. Okay, so doct is a Cartesian two category. So you
Mm-hmm.
might look at what are the pseudomonoids in there.
Okay.
And the symmetric pseudomonoids are actually quite interesting. So um, the
This.
symmetric, I guess in brackets,
Mm-hmm.
uh, pseudomonoids in
Uh,
doct,
yeah.
like specifying the structure of a symmetric pseudomonoid for P
Mm-hmm.
as an object
Yeah.
is equivalent to endowing C and D with monoidal structures that turn them into monoidal double categories.
Okay. Okay. So I feel like I need a sublist here. So symmetric pseudomonoids in double cat, is that what like a pair? So oh wait,
Yeah.
sorry.
So yeah. So you're making C and D monoidal double
C,
categories.
D. Okay. So on components, you need to give. Okay.
Mhm.
Is there anything weird happening with if I say C op? So explicitly, I'm probably saying
It's
that
fine.
the op is a
The op
pseudomonoid.
doesn't really
Okay,
go.
sure,
Yeah.
sure.
So so we basically when we specify the structure of a symmetric pseudomonoid in doc,
Uh-huh.
we give C and D monoidal structures
Yeah.
and we make P Lax symmetric monoidal functor with respect to those structures.
Oh, right. Okay. A lax symmetric.
Yeah,
Okay. Right. Okay. Right. Because they're looking at lax transformations. Sure.
yeah.
Sure.
So
Okay.
lax symmetric monoidal structure on P.
Okay. Lax symmetric monoidal. Okay. And monoidal structure. And I know that that sort of quite complicated structure, right? Because you've got the interaction with the compositors for the pseudo double functor and so on. So double pseudo functor,
Yeah,
sorry.
yeah. So
Um,
we're only looking at the the monoidal structure for those pseudofunctors,
right,
which is, of course, a separate thing from the
right,
laxity of the double functor itself.
right. But isn't there some sort of complicated inter? Oh,
Well,
uh, right.
you
If
you
you
just
you
have
break
to
all that, yeah.
unravel, yeah,
Okay.
what do you have? Uh, and P there goes from C up to
Oh
D,
yeah.
so we need to add it on there. But yeah, so the gist of it is that if you have a monoidal monad in
Mm-hmm.
dot, then you actually have first
Oh
a
right. Okay.
coalgebraic-modal extension sort of context.
So and by a monodal monad in dot, we say we've got dot. We form another
We have a
pure category.
monoid, sorry, we have a monad in dot,
Uh-huh.
and therefore, comonad in C and monad
Yeah.
in
Yeah.
D and the lax monoidal map.
Mm-hmm.
But this monad is monoidal,
Mm-hmm.
and so by point 3,
And that involves like the underlying the underlying endo functors are presumably monoidal functors plus some conditions on like the uh the units and multiplication for the monads and
sorry, say that again. So
well, sorry, a monoidal monad is sort of a um it's
yeah, I
there's
get
a
it now.
bunch of
Yeah, yeah.
like
So
ducts for that. Yeah.
there is compatibility conditions between multiplication and the monad
Hmm.
multiplication, like monadic
Right.
multiplication and monoidal
Monoidal. Yeah, yeah,
multiplication. Yes, yes, and so on.
yeah. Okay.
Yeah, there are some equivalent things. So like you can talk about tensorial strengths and all of that, but
Right. Yeah.
I don't want to go into that.
Sure.
But yeah, so the point is, if you have a monoidal monad in dot, you have all the things you might want to think about, right? Because you have these coalgebraic hyphen modal extensions
Mm-hmm.
that you can in fact extend to this sort of temporal logic on system situations that we want by taking Eilenberg-Moore objects.
Mm-hmm.
And if you want to talk about whether Frobenius holds, well, you need to have a monoidal structure on P in order for that to hold.
Yeah.
And that's where you get the monoidal structure.
Mm-hmm.
And yeah, so that's the bit that is not super resolved yet is this bit with Frobenius because, this monoidal structure is not necessarily a monoidal structure that you want to be asking about Frobenius for, right? We had this discussion before. So
Oh,
like,
right. Yeah.
I will have to wrap up
Mm-hmm.
in the next 5 minutes, but just to tell you what the sort of current difficulty is, let's say for a moment that P is the bare bones doctrine.
Mm-hmm.
So it's on set. I don't have any connectives coming from P.
Sure.
And L is my free Boolean algebra monad.
L is a free Boolean algebra monad. Sure.
And I want to ask for Frobenius for the conjunction, the Boolean conjunction.
Okay. Yeah.
So that means that my monad added a connective, and now I want to ask Frobenius to hold for that monad. Sorry,
Right.
for that connective.
Right. Sorry. So D is set here. Is that the
D
A?
set.
Okay.
Yeah.
So I've got some category. I associate each object as a set of primitive propositions. Freely extend that to Boolean algebras.
Yeah.
And I want Frobenius property for the conjunction. Did you say?
For
Yeah.
that conjunction. So I want Frobenius for the conjunction induced by the monad.
Mm-hmm.
So how do I do that? So in principle, you would need it to be the case that the monad itself is such that its fibers, so sorry, its algebras, or at least the free algebras, are always monoidal structures. So in
Hmm.
this case, which is the case here, right?
Yeah.
So
I mean, in multiple ways that
yeah,
Monod structured.
and we want that monoidal structures to be the ones making the associated monad in docked be a monoidal monad.
Ah, okay. So here, when we're looking for the lax symmetric monodal structure on C and D, that's like saying my category of contacts has products and like set has products, but these don't have anything necessarily to do with the like products in like endowed by the monad
Yeah.
L. Okay.
So that's one of the mysteries that need to be resolved. Like, do
Hmm.
we want to ignore Frobenius whatsoever in this case and say
Hmm.
this is an extra condition that comes afterwards?
Yeah.
Or is there like a sensible way to bundle this all together? Or, and I think that's maybe I'm misunderstanding him, but I think that's one of the things that David has in mind. Maybe you induce the stuff that does satisfy Frobenius from the outside by adding some more data. So something like specifying a wiring diagram for your system should give you a connective that you can ask about Frobenius.
Okay. Right. It does, now that you're describing it, it does seem like for the Frobenius property is a bit more like this, like we're really only interested in L's which endow your D with a monodal structure and like
Like you
they're
either do
yeah,
that or you impose that afterwards
right,
externally as an extra thing, right?
right. But like there are many like the Boolean algebra example, there are multiple monodal structures, so like you need to specify
Yeah, there are
you know.
multiple connectives, right? So
Hmm.
which one of them? And it's not clear how, like, there is no well, I guess, yeah.
Yeah, what if you choose conjunction over disjunction? Is it
Although you could say that Frobenius actually holds for all the connectives for Boolean algebras.
oh okay.
Um, I guess that is
Hmm.
probably true. It's certainly true for disjunction because left adjoints preserve. Um, anyway,
Hmm.
I'll have to wrap up now,
Hmm.
but hopefully you got a sense of what's going on.
Yeah,
So yeah, so
can
we
I get
have.
like a quick summary of
Mhm.
okay, so you're taking existing hyperdoctrines, you're expressing them in terms of double categories, which sort of simplifies some of the extra data or it folds it into the data of the map P, and then you're expressing and you want to look at taking such a thing and like adding some coalgebraic structure on the left and some modality on the right simultaneously to upgrade your, you know, the hyperdoctrine you start with is something more expressive. And you've got like a nice way of describing what those like pairs of extra structure are. They're just monads or symmetric monodal monads in this nice two category you can define quite generally. Is
Yeah,
it?
and the thing is, whenever you have such a symmetric monoidal monad, you would have such a way of like extending to systems by adding modalities on the logic as well.
Mm-hmm.
And then you might think, okay, so I just need to produce examples of those. And that's why this characterization is nice, right? Because, if you have a lex monoidal, lex functor, it will map
Monodal
monoidal
lex, yeah.
monads to monoidal monads.
Uh-huh.
So if you have any other, symmetric monoidal two category,
Mm-hmm.
you can look at what monoidal monads are in there,
Mm-hmm.
and all you have to do is describe a like symmetric monoidal Lax functor into docked in order to build examples.
Right. Okay.
And one
That's
of the
quite cool.
ideas is maybe we can do that for lenses, for example.
Okay. Interesting. Yeah, I would be interested in chatting more about like the examples you have in mind at some point. That sounds quite interesting, but I guess we'll have to stop there. Um, thank you.
Thank you, Jason.
Okay.